Okay, so this is the last class of the course. It'll be a short class where we'll give a conclusion to the topics that we spoke about during the year. So we saw this is the structure of the course where we started talking about local data processing, and then we spoke about distributed systems, then distributed data processing with respect to static data using Hadoop and Spark, and thereafter dynamic data with Kafka. And in distributed data management, we spoke about Elasticsearch for indexing documents. And we spoke about NoSQL systems for managing structured or semi-structured data. So in terms of distributed systems, we learned about client-server models. We learned about availability, transparency, three-tier architecture, and so forth. In processing semi-structured information, we spoke about MapReduce and Hadoop and Pig and Spark and HDFS and so forth. And with respect to storing unstructured information or text, we spoke about search, ranking, TF-IDF, PageRank, heaps law, and so forth. So we covered all these concepts. So the last part of the course was on NoSQL, where we spoke about storing semi-structured information like Cassandra, NoSQL, Neo4j, and so forth. We spoke about the CAP theorem. So at the start of the course, we spoke about the value of data, and hopefully through the course, you've seen somehow the value of data in action. You've worked in your projects and you've worked in different labs where we've seen this. And we also spoke at the start about the Twitter architecture, where essentially we had all these different elements used to build the Twitter technical architecture, where we had Hadoop for batch computing. You should hopefully all know what is Hadoop now. We had Redis for NoSQL, and we had Earlybird for indexing text. So Redis is a NoSQL system. We didn't see Redis specifically, but it's an instance of a NoSQL system. And Earlybird effectively is a Lucene clone that's essentially very similar to Elasticsearch, which we saw in the course. We didn't touch the part about the mobile applications, but okay. So many of these tools that you would have seen are in use, or variants of them are in use in different web applications or different web systems. For example, in Twitter or in Google or Facebook or YouTube or Dig or what have you. So hopefully as well, you got some experience with working with large data sets, which is not so straightforward. If you make some mistake, oftentimes you'll have to wait maybe 2 hours for that mistake to become clear. So there are different strategies, testing on small data sets first, before running something on a large data set, for example, and obviously using some of the existing frameworks that are already there for managing or working with large data sets, such as NoSQL systems or processing frameworks like Spark and so forth. We also saw some of the values and some of the challenges of distribution, where if we can use lots of machines to accomplish a task, then we can deal with larger data sets and we can deal with larger data sets more efficiently in less time. However, this creates some challenges. What happens if a node fails, if a machine fails, if a hard disk fails? So this creates some challenges, some difficulties. So for frameworks, we discussed some distributed processing frameworks. We discussed Hadoop, Pig, Giraffe, and Spark in the labs. So hopefully these are very useful frameworks that hopefully you'll find useful in your future careers. And we also saw some NoSQL systems. So we saw Cassandra, Neo4j, Elasticsearch, and MongoDB. Okay, so in terms of the more conceptual parts of what this course is useful for, probably you've heard of data scientists or data science. So we can try to relate some of the concepts of this course with the data science career in general. So as we see here, data scientist, the sexiest job of the 21st century. I'm not sure about that. This is from 2012, but in any case, this is what the Harvard Business Review thought at the time. So they stated here that the shortage of data scientists is becoming a serious constraint in some sectors. So we can look at some of the job postings. These are analysis of offers of jobs for data scientists, and we can see how it might relate with what you saw in the course. So this one's from 2016, and it mentions SQL as the top skill. So hopefully you saw SQL in a database course. We see Hadoop, number 2. We see Python, number 3, Java, number 4, or number 5, Hive, number 6, MapReduce, number 7, NoSQL 8, and Pig 9, and SAS 10. So of the things that we saw in this course, we saw Hadoop, We saw Java, okay. We saw something similar to Hive. We didn't see Hive itself, but we saw Pig, which is kind of the same idea. We saw MapReduce and we saw NoSQL. So we saw probably 6 of the 10 things that were listed here in this analysis from Crowdflower. From Forbes 2017, picking out the ones that we saw in this course again, Hadoop, Java, Spark for the first time is appearing, Hive, which we didn't see, but we saw something very similar. So we see good representation again. Tableau is for visualization. I'm not sure if you've used Tableau in another course, but SAS is more for business analytics. There's something interesting here, which I'll try to explain as well, which is why do we have Java and Python and OR? So these relate to 2 different aspects of data science that I'll discuss soon. So one from 2018, not to go into too much detail, but we have Hadoop, we have NoSQL. Okay, maybe you saw a little bit of Scala. We have Spark here as well. We have Hive, okay, Pig, Cassandra, MapReduce, and so forth. So we see a good representation of the things that we saw in this course. Again, we see Spark, Hadoop, Java, AWS, which is Amazon Web Services, which is similar to a cloud-based platform that you could apply these technologies on for Amazon, and Azure, which is Microsoft's cloud solution. So it's similar to Amazon. So we see quite a good representation. So this analysis I quite like from 2020. It's the most detailed one I found. So we see Spark and again Hadoop, and we see Spark getting more and more important than Hadoop as well. So we see a lot more machine learning sort of stuff, PyTorch, for example, TensorFlow, these sorts of things you might have seen in other courses for machine learning. What's interesting about this analysis is that they also try to factor them. So they try to somehow identify different types of profiles. And here they identify 3 profiles, which is data engineer, data scientist, and data analyst. And this is a pretty interesting categorization because we see that in data engineer, we see the darker colors mean more emphasis for these sorts of jobs. So this data engineer role, we see that Python is quite important, SQL is quite important, Spark is super important. Being able to work with distributed systems in AWS is important. Scala is important, probably because of Spark. Java is important. Hadoop is important. And the machine learning stuff, less important. We see for data scientists that Python is super important. And SQL is moderately important. And then we see there's less emphasis on things like Spark, although it's still important, AWS and Scala. And then finally, data analyst, or Excel is important, SQL is important. OR is kind of important, Tableau is important. So what are these jobs? So data engineer typically means the sort of stuff we did in this course, which is take a large data set, prepare it, aggregate it, apply some queries, extract some information, and so forth. The data scientist role here, what it refers to is mainly using machine learning types of tools, to use Python, to use OR, to use to take some data maybe that's already been pre-prepared and to analyze that from a data science perspective. And the analyst role, the analyst is somehow between, is maybe someone who's not necessarily a computer scientist, but somebody who understands a bit, who's between the business role and the data people. So they can take the data, they can visualize them using Tableau, for example, do some aggregations or some graphs in Excel, maybe do some hacking in Python and so forth, and do some queries for analytics in SQL. So these also correspond to what my intuition of this area kind of entails. So we have data engineering, which is kind of this course in SQL and databases. We have data scientists, which covers more like, let's say, for example, machine learning type roles, or maybe hacking some scripts in Python. And then we have the analyst role, which is mainly the sort of business side, visualization, reports, business analytics. Yeah. Oh, sorry? Interpretation, yeah, like taking or trying to maybe relate with the data scientist to say what we need for this business is this sort of, we need to know how our experts are doing in this region. And then they'll take the data from the data scientists, the data engineers, and try to visualize them. Yeah. So this is not like super, super concrete or well defined, but there are kind of 3 interesting profiles here that make sense to me in practice. Yeah, so mostly what we've seen in this course is a sort of engineering part, where we see, for example, Java plays a bigger role because, Python is also important here, but Java plays a bigger role for engineers because it's a more efficient language for dealing with large sets of data. Same for Scala here. It's more efficient language than Python. Okay, so this is 2021. I think this is the last one I have, and we see again Python, SQL, or Spark, AWS, Java, Tableau, Hadoop, TensorFlow, Scala. So we see Java and Spark here represented. No, SQL's not here, which is unusual, but okay, and Scala. So the conclusion of that is just that we've learned a lot of practical kind of frameworks and tools and languages that will be quite useful, hopefully, to you in your future if you go into a data science, data engineering type career. So in general, these frameworks are of importance, but also it's the underlying principles, the ingredients that are important behind these tools. There are so many tools that it's not enough to know the different tools, but also to know what makes them, what are the characteristics of those tools and what makes them useful for different types of settings. So to understand more the ingredients as well as the recipes, the final recipes. So as a second last part of the course, we're going to look at some typical consultancy questions. So if you ever wanted to do consultancy in big data, you could earn a lot of money. So if you like the smell of money, this is maybe not a bad job to have. Even not being a consultant, just being in a company, your company might face certain problems. It might face certain challenges where they'd like to know what kinds of tools we should use. So an important goal, I would say, of this course is to maybe to try to understand when to use what tools we saw in the course for what specific settings. So we'll look at a few examples. We'll go through them quickly, but hopefully we can figure out what to use. So I've crawled 30 million job postings and I want to perform a word count. Well, what should I use for this? MapReduce, okay. We could also use Spark. So in this case, I would say this is a sort of a trick question, because if we want to do a word count, we could probably just do it locally. So if we could just do it on my notebook, or it would be easier, right? But otherwise we could use Spark, maybe, for example. We could also use MapReduce, but it might be a bit slower, but it will also be fine. Yeah. Yeah. So my website has 120 million users. Each user has personal profile data, photos, and friends. I have 12 machines available. What should I use to answer queries for generating my site's web pages? So in this case, since we want to answer queries, so we're given, for example, a user ID, and we want to get their information immediately. So we rather want to use the data management side. So a database. So would you use SQL, Neo4j, Cassandra, MongoDB?
We started in a lab. I don't remember.
Yeah, there's also a trick here, because we saw this in Hadoop as well when we discussed Hadoop. Yeah. So in this case, since we want to do queries, we could probably use NoSQL for this. So why would we use NoSQL? Because the request will always be of the same type. It'll just be like a user ID and give me back all the information about that. So we just have a key and some values. Yeah, so we can use Cassandra, maybe, or MongoDB, for example, would be pretty good, or Elasticsearch or something like that. Yeah. Okay, my company has 30,000 employees, and we want to store and query information about bank accounts, insurance, etc. What should I use? Not necessarily from this course. Postgres, yeah, SQL. Yeah, so we have no reason to use anything from this course here. The scale is not an issue. The queries might be quite diverse, so we don't, it's not just given an ID of someone, get back some information. It's not for a web page. Reliability and ACID are super important here, so we might want to use like a relational database management system, maybe mirrored, so we have two machines doing exactly the same thing. So MySQL, Postgres, this sort of stuff. Yeah, exactly. And you have ACID, and you have SQL, and you have all the nice stuff of relational databases. So this is a sort of case where, sometimes we don't want to use NoSQL, and this is an exact case where we don't want to use something like we don't want to use something like MongoDB or Cassandra. We want to use Postgres or MySQL or Oracle. My telescope is generating millions of images of the sky every night, but I'm only interested in finding some images that may indicate supernovae. What should I use? We could use Elasticsearch, yeah. So there is one aspect here, which is that it's dynamic data. So it's generating millions of images of the sky every night. So,
like Twitter.
Yeah, like Kafka. Yeah. So we could use, in this case, Kafka. So we could use a streaming platform. We could use something else behind that. We could use the Elasticsearch, or we could use some other indexes, some document store, maybe to store the data. But for the initial processing, we need some way to just process, filter, and redirect this stuff. And this would be Kafka. So this is the astronomy department here. There are people working in the astronomy department that use Kafka for processing astronomic data. Yeah. So I'm scraping data about video games and their characters from various wikis. In total, I've scraped information from about 1 million pages, and now I want to be able to search over what I have, for example, to find all non-human characters in a particular video game or platforming games featuring plumbers. What should I use? Yeah, I would say so, yeah. So I would say we don't want to use Cassandra here. We don't want to use Cassandra because we don't know what we want to query. It's not clear if we want to query, if for Cassandra, we have to be very specific on these are the sorts of queries we want, and we have to build a table around that.
Yeah.
Here, we don't have that. We have some sort of more open domain where we don't know what we want to query. We don't know how the data will be structured either. So we need something more flexible, but also we need some sort of expressive query language that will allow us to do joins, for example, yeah? Neo4j could be a good option as well, yeah. If we had a lot of text, Elasticsearch could be good, MongoDB could also be good, or we could also consider a graph database. Using a relational database here would be tricky because we'd have to define the schema, and that schema might evolve over time. So it's not so straightforward to use Postgres here, for example. I have descriptions of millions of patents, and I want to create a system to find the key patents relating to a given technology or application. So if we think of patents, patents have a lot of text. Yeah, so these patents are just these descriptions of some invention, maybe with some images and so forth. So if we have a lot of text, probably the best system here to use would be. No, in this case, I think it's mainly since you want to find, so this would be real-time application where the user is like, entering a search, and then they want to get back a list of the top patents that are related to that. So they could search for bathtub, for example, and they should get back a list of results of all the patents mentioning a bathtub, maybe ranked by importance, for example. So this is more going into the stuff we saw for Elasticsearch for information retrieval. So we will index the content of the patents, maybe with some fields and inverted indexes. We want some relevance ranking. If we search for bathtub, we want to know that the patents are relevant to that, and also some importance using PageRank. So PageRank because patents cite other patents, so we can use PageRank to determine importance. Given GPS billing information of mobile phones, weather updates, accident reports, time of day, historical data, and city maps, I want to plan the best routes from A to B. What should I use? So again, a major aspect of this, if we think about it, is the dynamic part. Yeah. So for that, it's similar. We could use Neo4j. In this case, it could also help with the best routes from A to B, although it's not specifically designed for that. It could find paths. So I would say that the first element that we want to use to gather all this information together and organize it would be Kafka. Yeah. So we could have Kafka, and then in the background, we could use something like Neo4j or some other connectors to store. Yeah. But principally Kafka here for the streaming platform. So I have information about tens of millions of papers and millions of movies, and I want to compute the Erdős-Bacon numbers for all people. So this guy here is Erdős, and this guy here is Kevin Bacon. So the Erdős number, Erdős was a famous, I think he was Hungarian mathematician who basically spent his whole life traveling around working with different people on different problems. So there's this notion of an Erdős number, which is basically, if you're Erdős, you have an Erdős number of 0, and if you co-authored with Erdős, you have a number of 1, and if you co-authored with someone with a number of 1, and you don't have a number of 1, you have number 2, and so forth. And then Bacon is the same thing, but co-acting. So Bacon has a number of 0, people who acted with him number 1, and so forth. And then Bacon is the maximum of both. Yeah. Okay. So we want to analyze this. So we have tens of millions of papers and millions of movies, and we want to compute the Erdős-Bacon numbers for all people. So that means a sort of a batch processing, right? Yeah. So what would we use?
we think about the distance, they think about Neo4j.
Yeah. So the issue with Neo4j here is that if we want to do this for all people,
Yeah, that's what,
it's not going to work. It's a transaction type real-time database, so it's not good for this. It's like a
yeah.
you could try it with SQL as well, and it could actually work with tens of millions, but it would be at the limit. So what I would recommend here would be to use something like Spark or MapReduce. So Spark would be better because it's recursive. But an even better option might be to use a specialized graph processing framework like Giraffe or GraphX. So we saw a Giraffe in one of the labs. So this would be good. But if this question were slightly different, and if we were to say that I want to compute the Erdős-Bacon numbers for a specific user, like users come and they query, then it could be a good option to use something like Neo4j. Yep. I think there's maybe two more of these. So I'm collecting information about research networks in Latin America. I have information about author affiliations, publications, topics, etc. Given a particular user, I want to recommend collaborators in the region based on the co-author network of that user. So what should I use?
that's what we use.
Yeah. Yeah, I would say you could use Neo4j for this. Yeah. I mean, you could think as well about pre-computing heavily. You could try to pre-compute, like for every author, have recommendations using Spark or Giraffe or something. But here you could probably use Neo4j. It depends on how costly the queries are, but I think Neo4j could be a good option. I'm working with a company that has a web application used by more than a gazillion users every second, so lots of users. Sometimes new software is deployed that can have bugs, turning some users away. I want to monitor and search over logs for recurring errors that might be affecting our user experience. What should I use? So this use case is super common in any large company that they want to do log monitoring. Yeah, so there's a lot of text. These logs are typically like some error message and so forth. There's some structure to it. But in general, you should be using something for dynamic data, first of all, and then also something that can provide search. So since the logs are streaming all the time, since we would Kafka, yeah, perhaps. And then we could use some distributed inverted indexes to search over the text, like Elasticsearch or Solr or something like that. In the case of Elasticsearch, there is the mean stack. No, mean stack is different. That's JavaScript. What's the name? Elk. Elasticsearch, Logstash, and Kibana. There's a specific set of tools around Elasticsearch for specifically this use case, which is a super common use case. Most large companies want to monitor their web logs and see what's going on. So these would be some good options. I'm working at a cinema. Given a large collection of movie data like IMDb, I want to compute profiles for people who work in movies, including how many movies they have directed or starred in, what are the average ratings of the movies, their most frequent collaborators, awards won, and so forth. Afterwards, when a user visits the cinema webpage, they can hover their mouse over any person to view that profile. So you want to enrich a cinema's webpage so people can hover on an actor and get all this profile of information about them. In this case, it could be, yeah. So in this case, if it was based on a specific schema, we could use SQL for this probably, yeah. In this case, I would say, given that it's a web page, and given that for a given actor, we know all the information we want. The query doesn't change. That we could use like a NoSQL system. Yeah, we could pre-compute, but it depends on the scale. Probably there would be no problem using a relational database here. So if we wanted to be super efficient for our queries, like if we had lots and lots of users visiting our webpage and we wanted to optimize it, the idea would be to pre-compute all the answers. So we could use MapReduce or Spark to compute all the profiles. So given some actor ID, we get their profile, and then we just index that into something like Cassandra, and that would work well. Okay, so these are kind of useful things to think about when you're working in different companies or whatever. I think it will be good to be able to choose the right technology. That's sometimes the hardest part, is to say, okay, we should use Kafka for this, or we should use Cassandra. Yeah, it's challenging. Yeah. So these are some of the scenarios. Then there is the final exam of the course. The final boss of the course is the following. Let's see. Hopefully you see this as well in Zoom. So this is called Big Data or Pokemon, where you have to guess which thing is Pokemon, which thing is Big Data. Any ideas? I don't know. Do we have, usually we have some Pokemon experts. Pokemon, we go for Pokemon. Yep. It's one correct. Pangul. Pokemon? No. I have no idea what Pangul is, but Delibird. You got Pokemon again? Yep, correct. Akibon. Yeah, I think that's correct. No SQL database with object-oriented storage. Geodude. That's easy. Geodude. Phoebus. There's a Pokemon. Arbok. Pokemon. Impala. I don't think so. It's big data. Seahorse. It's big data, yeah. I think there's Horsey, which is it's almost a trick question, yeah. Not to be confused with Horsey. So seahorse is big data. Azkaban. So Azkaban, sorry? Pokemon. No, big data. It's hard, no? Arabas. Big data. Azuril. Big data. No, Pokemon. Titan. This one I actually know. So that's a hint. Yeah, it's a graph database. It's like Neo4j or yeah, I do. Hopefully everyone thinks this is big data. Otherwise, we have to retake the course. Flink.
That's a big data.
Yeah, it's a streaming platform like Kafka.
Yeah.
Pokemon. Yeah. Hackathon. I'm not sure how many more there are. I think there's 20 in total. No. Big data. I don't remember it either. Tokutech.
Big data.
Big data. Yeah.
Okay.
Atlassian. It's big data, but we'll get it inaccurate. But it's not really big data. It's just this Jira. Have you heard of Jira? Jira issues. It's like an older version of GitHub issues or something like that. It was run by this company, Atlassian.
Yeah, that's a Pokemon.
Yeah, we saw that one already. And Geode? I think it might be Geodude. Yeah. So Geode is big data. There's some tricky ones in here.
Big data.
Yeah. I don't know what that is. Yep. Arvados? No. I have no idea what it is, but it does. The logo as well looks like one. Vulpix? Yeah. Since Devesium? No. I've never heard of it either. Not to be confused with Meganemium. Summingbird? I think it's another trick question. It's big data. Twitter technology combines streaming, MapReduce, Scalding, Scala, and Storm. So it's some sort of streaming data. Okay, so we got 59% correct.
I still get through, right?
Hey, no, you still passed. That's okay. Everyone passes. So I think we've gotten before 100% right, but mainly because there's been some experts on Pokemon who know all the Pokemon, so they just say Pokemon, not Pokemon, Pokemon, so forth.
So I don't remember.
Yeah, it's tricky. So okay, so that's how do I get at it? Yeah, so that's the final exam. Very, very good. And that's the end of the course. So hopefully you've enjoyed the course. And yeah, hopefully you've learned a lot. So I guess what's left in the course, the projects have been submitted. So yeah, so today I'm gonna upload the videos and we'll share out the JSON forms for evaluating the projects. I think that's about the last thing that's left. So yeah, hopefully you enjoyed the course. Yeah. Any questions maybe? Any questions in Zoom? If not, best of luck with the rest of your semester. Good luck with the exams and all of that. And we'll be in touch. So there's a couple of things. Yeah. So there's the projects. There's a couple of other things. So another thing I wanted to share or to get your feedback on is to do a survey on ChatGPT. So ChatGPT is a relatively new phenomenon. We've not had a policy for ChatGPT here, but it seems that ChatGPT could be used to solve a lot of the labs. So we're going to do Google Forms, and the idea is just to get information. We just want to see how much people were using ChatGPT and what they think about it for future versions of the course. So we'll see how that goes. Okay, so if there's no other questions, best of luck with your exams. See you guys in Zoom.